Welcome back to Physics 141 Online. We're now moving into a new section of the course where we're going to study some really interesting physics relating to the interactions between objects, especially in the case of collisions. And to do this, we'll be defining a new physical quantity called momentum. But first, in order to introduce momentum and explain why it's significant, we're going to talk about the center of mass of an object. So the definition of a center of mass, if you have a collection of particles that all form one system, is that it's the mass weighted average position of all the particles. So if we have these three masses, m1, m2, m3, and they're sitting in the xy plane, then we can define the x-coordinate of the center of mass of that three-particle system by taking each of their x-coordinates, the x-coordinate of particle 1 multiplied by its mass, the x-coordinate of particle 2 times its mass, and particle 3, its position times its mass, and add those up and then divide by the sum of the masses. And so if we do this, it's going to calculate a position. If you look at the dimensions, you'll get a position here because the mass terms, the units will cancel out, but that position will be weighted by how large those masses are. If mass 3 is much larger than the other two, then the x-coordinate of the center of mass position will be fairly close to mass 3 because it has more weight in the overall answer. We can symbolically write down this x-coordinate of the center of mass using summation notation like this, and we'll use capital M to indicate the total mass of the entire system. And of course we can do the same thing completely analogously for the y-coordinate of the center of mass, and if these particles had different z-coordinates, then we could do the same thing for the z-axis. So that's the definition of the center of mass. In vector notation, which is going to make things nice for the derivation that I'll do in just a minute, let's write this, instead of having to write separate equations for each coordinate, let's just write down the vector position of each object as r1, r2, and r3, because those r vectors have within them the x and y coordinates, so that we would get the sum over all of the particles of the mass times the particle position divided by the total mass of the system. And so, as I said, each particle has a position given by that r sub I vector, x sub I hat plus y sub I j hat. Now, that's the definition of the center of mass, but what about its motion? What good is it to talk about the center of mass? Well, we can take our definition of the center of mass position and very simply calculate the velocity and acceleration for the entire system, the velocity and acceleration of the center of mass. And we'll see some interesting properties that it has. So the velocity of the center of mass would be given by differentiating the position of the center of mass, and each of the terms in the summation, which originally were the mass times the position, would become mass times velocity. So that's the velocity of the center of mass. And one more time, if we differentiate each of those terms, we would get the acceleration of the center of mass. So the derivative of mass times velocity would just be mass times acceleration. And so, using Newton's second law, we realize that every term in the numerator of this expression is the mass times the acceleration of a particular particle, which is the net force on that particle. So we're going to replace ma by F sub I, understanding that F sub I represents the total force on particle I from all sources, whatever is acting on it. Now this leads, if we take the equation on the upper right here and we just rearrange it by multiplying both sides by the mass, we can take that and rewrite it as the sum of the forces on all of the objects that are in the system is equal to the system mass times the acceleration of the center of mass of that system. And so one thing we can do to simplify this a little bit is realize that for each of the particles, the net force is going to be a sum of terms, each of which is either an internal force, which means it's exerted by something inside the system, or an external force exerted by something outside the system. So let's take this sum over all the particles of the force on each particle and break that apart into a sum of external forces and a sum of internal forces. So that's still equal to mass times the acceleration of the center of mass. Now, internal forces, what that means is if I have a three-particle system, particle 1 exerts a force on particle 2, but then particle 2 exerts a force on particle 1. And according to Newton's third law, those third law pair forces add up to 0. So all of the internal forces in the system, using that reasoning, will add up to 0, leaving only the sum of the external forces acting on all the particles of the system. So now we've got something that actually is quite profound. What it tells us is, however we define our system, the mass times the acceleration of the center of mass is given by the sum of the forces acting on the system from outside. And this is exactly an expression for Newton's second law for our system, provided that we understand that it's the acceleration of the center of mass, and therefore the velocity of the center of mass and the position of the center of mass that's important. And so another way to say this is that the center of mass of a system of many particles behaves just the same way that a particle with the total mass of the system would behave if we were tracking its center of mass position. And so we can illustrate this quite nicely using some examples that are shown in the following video. So take a look at this and I'll stop it and explain what's going on at a couple different points. Here you can see two professors or two assistants who are tossing objects illuminated just under normal white light against the backdrop of a projector screen. And these are objects that are asymmetrical. Okay, so those objects, as they were moving, you could see that they were wobbling. There was some kind of rotational motion going on as they flew through the air. But now what we'll look at is those same objects tossed under black lights, where the center of mass of each of those objects is painted orange. So look at that. The center of mass moves in the same kind of motion that a single particle would move in the normal case of free fall or projectile motion. And this is a visual demonstration of that equation that I just showed. Here's also an interesting case because the fellow on the left is going to throw that wheel where the center of the object was painted. Okay, and you could see that that dot was wobbling because the object's center was not exactly the center of mass of the system. Now the fellow on the right is going to throw it back to the left where the center of mass has been indicated with a dot. So all of that just to show once again that this equation here got to shut it off. Got to remember to do that. So that equation that we derived is telling us that we can treat a more complicated system of many particles as if all the mass is located at a single position, and that position is that of the center of mass. So from this fact, if we call that kind of a system where if we define a system of particles where the net external force is 0, we can call that an isolated system, and from that we can take our equation for Newton's second law and realize, hey, if that summation adds to 0, then what that means is the acceleration of the center of mass is 0, and if the acceleration is 0, then the velocity of the center of mass is a constant. All right, and this is a very useful result in characterizing the motion of a system that's isolated. And then a very special case of an isolated system is one in which the system is initially at rest, so that its center of mass velocity is equal to 0. If that's the case, if we have an isolated system whose center of mass is initially at rest, then the center of mass will always be at rest, and the center of mass position will always be constant, right? Because if the center of mass isn't moving, then its position will always be constant. And there's a classic kind of problem, sometimes called a Canoe problem. And I'm going to skip over this for now because in class I'll work this out as an example. But the idea is, if you have several people in a canoe, and then if they move around and change places within that canoe, the canoe itself will move, but in such a way that the center of mass of the canoe will always stay at the same position. And so we'll have an example of that using this boxcar problem in class. However, for an isolated system, we can go on and express its special property in a different way. Alright, so we said that for an isolated system, the velocity of the center of mass will remain constant, and here is the definition of the velocity center of mass, where we have the sum of mv for each of the particles divided by the total mass, and rearranging that, mass times velocity of the center of mass is equal to this sum. And so when we say that the center of mass velocity doesn't change, it's constant, that means that this summation is also constant. And that's a very interesting fact. We have something which, if we sum it up over all the particles in the system, it remains constant. And when physicists find something like that, they find something that's constant, they get excited and they attach special importance to it. And in this case, we even give it its own definition. So mass times velocity, where velocity is a vector for an object, we define that to be p. P is a vector, and we call this the momentum, or more accurately, the linear momentum of the system. This is to distinguish it from something that we'll define later for a rotating system that we call the angular momentum. Alright, so if we recognize this definition, that the sum of this term added up for all the objects of the system is equal to a constant, then we can write down the law of conservation of momentum. And it's very simply just this. If that sum, mass times velocity, is a constant, then that means whatever it is at some initial location or at some initial configuration, it will always be equal to that value. And so if we have an initial situation and then a final situation for two or more objects that are that make up a system, then we can set those two things equal to each other. And that helps us understand a lot about how a system evolves its behavior in time. So remember, though, in this equation, and when we start to do examples involving the motion of objects or collisions between objects, remember that these momentum terms are vectors. And so when we write them down, we have to take into account the direction of the momentum. And it's not enough just to write down m times v. We have to take the direction into account. So the great application of the law of conservation of momentum is in analyzing collisions. Collisions are simply ways in which particles in an isolated system interact with one another. Sometimes the particles will physically collide with one another, such as when we have balls on a pool table or pucks on an air hockey table. But you can also have situations where objects exert forces on one another without touching. For example, the sun and the earth. They form a system, and they interact with one another and attract one another without actually touching. So, before we work through some examples, though, let's define the different types of collisions that we can have. And they're broadly broken into two different categories. One is that of elastic collisions. For elastic collisions, not only is the total momentum of the system conserved, according to the law of conservation of momentum, but the total kinetic energy of the system is the same before and after the collision. And so what this is saying is the collision happens in a way that no energy is lost in the collision. And these are called elastic collisions because if the objects are elastic, then although they may touch each other, that they spring back and they regain any energy that caused them to deform. But the second category of collisions, and this one is much more common in the real world, is that of inelastic collisions. In an inelastic collision, linear momentum is conserved, just as in an elastic collision, but the total kinetic energy is not conserved. It's always less after the collision than it was before. And this implies that some kind of energy was lost in the process of the collision. The objects are not elastic. They deform in such a way that some of their initial energy is lost and they don't have the same kinetic energy after the collision. And then in this group of inelastic collisions, there's one special case we could call 2A. And most textbooks refer to these as completely or totally inelastic collisions. And this is where the two objects that collide stick together after the collision. And so that kind of collision is particularly easy to analyze, because if two objects stick together, then after the collision they also move together, which would mean they would move off with the same velocity. And so that does simplify things for us. So we'll do lots of examples in this part of the course dealing with collisions of particles that make up an isolated system. And I'll see you in class.